So next up, we have a PhD student, Kavitha Chandrasekar from the University of Illinois here, and she is going to tell us about metabalance.
So my talk is about MetaBalancer for automated selection of load balancing strategies. I'm Kavitha Chandrasekar. I'm a PhD student, as Michael mentioned. This work was done by Harshita Menon, myself, and Professor Kale over the last semester. Here's the outline of my talk. I will begin with the motivation for the need for dynamic load balancing and strategy selection. Then I'll move on to the implementation in Charm++, which is primarily the implementation of MetaBalancer framework itself. And then I will move on to discussion of several mini-app application results. So first I begin with the question, why do we need load balancing? I think we've heard that from quite a few speakers today. There are several HPC applications that exhibit load imbalance. For example, there is the adaptive mesh refinement. The figure on the right is the AMR mini app in Charm++, which shows that in the refined regions, there's high computation load in the spheres, whereas there's much lower load in the other regions, which is a reason for load imbalance. There's also several other applications like molecular dynamics, where there's variability in the particles per computation unit. With load balancing, we can achieve high performance and also high resource utilization, consequently. Why Charm++ lends itself to load balancing is primarily over decomposition, which is the division of computation units into much more number of units than the hardware processing units that are available. This supports migratability of work units and making load balancing possible, and Charm++ supports a suite of several load balancers, which is of interest to us in this work. I mentioned the need for load balancing, but there's also a need for adaptive load balancing selection, primarily because the load imbalance is not always static. It varies over the application's run. And there's also variations in application characteristics itself. Even for a single application, there might be changes in characteristics with input data sizes over the phase of execution of an application run, or even when running an application on a different number of cores. Therefore, the need for choosing an optimal load balancing strategy. There's been previous work in MetaBalancer that performs adaptive load balancing by choosing the best load balancing period and triggering the load balancer when load imbalance is observed. The figure on the right is the Lassen application from LLNL, which simulates a propagating wavefront from a point source. And as you can see, as the wave propagates, there is load imbalance that's created in different portions of the region. So there can be, what are the differences in load balancing strategies? They could be due to communication-intensive applications requiring graph partitioning of the object communication graph in order to reduce the communication between chars, or it could be the main imbalance that we usually see, the computation-based load imbalance, which can benefit from different kinds of load balancers, which I will get to shortly. So these are some of the main load balancing strategies that we use in Charm++. There's the centralized load balancing strategies wherein all the object statistics is collected centrally and the algorithm is run centrally. The greedy LB performs from scratch load balancing of objects by making sure that a max heap of objects is mapped to a min heap of processors. There is refined LB, which takes into account the existing mapping of objects and then only migrates objects from overloaded processors to underloaded processors. Then there is hierarchical LB or hybrid LB, which is more useful for large core counts, where it performs load balancing in a hierarchical manner, where subtrees run greedy algorithm, whereas higher level nodes in the tree run refined load balancing strategy. There's also distributed load balancing strategy, which uses partial propagation of information and load statistics in order to map charge by moving charge from overloaded processors to underloaded processors. Since it's not centralized, it saves a lot of strategy cost. There are also several communication-aware load balancers in Jam++, like MetSLB, which performs partitioning of the object communication graph. Scotch LB, which also performs object communication graph partitioning, but in addition, it can also take load imbalance into account. There's Scotch Refine LB, which is a variation of Scotch LB, which takes existing mapping of objects in order to reduce migrations into account. Now we use an example to see how different load balancing strategies can affect a single application. Like I mentioned, different applications can require different load balancing strategies, but even a single application can require different load balancing strategies depending on various parameters. This figure shows Lassen, the wave propagation application. As we see, distributed LB performs best when moving to 512 cores and 1024 cores in terms of speed up for Lassen, but for 128 and 256 cores, we find that hybrid LB performs best. Other algorithms like greedy LB perform close, but as the core count increases, we observe that they are not as good as distributed LB. This is an example for a single application showing variation with weak scaling. Now, moving on to what metabalancer is. This work focuses on strategy selection. So how do we go about selecting the load balancing strategy that's optimal? So we begin by performing multiple runs. We take into account, we use a synthetic load balancing example LB test in our suite in order to tune several parameters and make multiple runs. And then we train the random forest model with these runs. This is done offline. And then since we have tuned it for several configurations, we assume that this model would mostly capture the application characteristics that we might come across in real applications. At the application runtime, then metabalancer captures these features for the application, and then it feeds the test data into the training model. It then generates or classifies the best load balancing strategy for that application. And this has very low overhead because the training has been done offline, and all the computation that needs to be done is just classifying of the test data for the particular application's run. Once the decision has been made, metabalancer is able to invoke the load balancer, and then this process continues, wherein if there is more load imbalance, it continues to capture application characteristics in order to come up with the best load balancing strategy in the future. So these are some details as to how metabalancer collects statistics. We avoid a high overhead collection by making sure that this is done asynchronously. Objects deposit load information at iteration boundaries. So these are the @sync calls that we use for load balancing usually. But in this case, metabalancer does not invoke a load balancer immediately, but only uses the @sync calls to aggregate information about objects at processors. like I mentioned, there's no waiting because once the at-sync call is called, the char can move forward. So one of the chars could have moved to third iteration, whereas the another char is only at the first iteration, but the reductions can still continue without having to have the application wait at each at-sync call. Then reductions are done asynchronously for each iteration to collect features. We collect about 30 features for performing strategy selection. So a little bit more about the random forest machine learning technique that we use. So this is a classification task, but it's not like a decision tree. It's a forest of trees. We use 100 trees for good accuracy in prediction, but we can increase the number of trees. It might slow down classification a little bit, but it might provide more prediction accuracy as our training data set increases. The nodes in each tree represent the features, and the associated threshold is calculated by the random forest training model. Leaf nodes are the load balancing strategy itself, which will be predicted by the algorithm. There are several tunable parameters like tree depth and the classifier to use in the random forest algorithm that we can experiment with to improve the accuracy of our model. So one question we have come across is, why not use a decision tree? One problem with decision tree is overfitting. And another problem is that it's harder to come up with the threshold value for each internal node that you're trying to classify with. In general, we use a decision tree in order to get a general idea of what are the scenarios in which different load balancing strategies are applicable. And then we use these features to train our supervised machine learning random forest model. Random forest model itself uses these, in our case, the 100 trees to find out the maximum weight that each tree provided to each load balancing strategy. So it's like a consensus of all the trees on which is the best load balancing strategy to use. And the trees themselves are constructed by using random sets of features at each node. And that helps in improving the accuracy of the model. This is the decision tree that we used for our purposes in order to understand which load balancing strategy would probably be selected. And this helped us narrow down the features that we should likely feed to the random forest algorithm. So if you look at the test data, you might want to decide if there's high load imbalance, that's when you actually want to perform any load balancing. Otherwise, you just decide on no load balancing. Once you decide there's high load imbalance, you decide whether the communication versus computation load is high. If there's more communication, or if it's more communication intensive, then you would go further down this subtree to figure out if it's topology sensitive. If it is topology sensitive, then you would want topology aware algorithms for your load balancing. If not, then you look to see if there's a high rate of change of imbalance. If the rate of change of imbalance is very high, then you might want to use graph partitioning algorithms that also are refinement based, so that when there's a high rate of change, you would want to invoke the load balancer several times, and you would not want to incur cost of a from scratch algorithm, which has a lot more migrations and is expensive in terms of migration cost. If the rate of change of imbalance is low, you would want to use something like Scotch, which also takes into account the load imbalance of the objects. If there is none, if it's primarily communication intensive, then you want to look at something that's graph partitioning like MetaSLB. On the right side of this tree, if it's compute intensive, if the load is focused on computation, load imbalance is all computation bound, then you want to look to see if there is, again, a rate of change of imbalance is high. If it's high, then you look to see if the migration cost is low. Because if it's high, it's preferable. If it's not high, it's it's okay to do something like greedy LB, which does a lot of migrations. But if the migration cost is low, you wouldn't mind doing refine LB. I mean, if the migration cost is not low, then you can do refine LB. And on this side of this subtree, you want to also check about large core counts. If the rate of imbalance is high and the number of core counts is also large, then distributed LB might be the way to go. However, the issues here are that we do not know what it really means when you say that the communication load is much higher than computation load, or what is the rate of change of imbalance at which you decide to go this side or that side. So we primarily use this decision tree in order to figure out what features to feed into our model. So these are some of the statistics that we collected. Some of them are processing elements related statistics, which include number of PEs, the PE load imbalance, PE average utilization, minimum utilization, maximum utilization. These are all aspects that we generally tend to consider when we are performing load balancing. And they're also part of the decision tree that we just discussed. Then there's the object statistics, which includes the number of objects that are part of the application, or the number of chars that is, what's the per PE object load. We also have migration overhead as one of the important aspects to consider. There's communication statistics, which are available through the communication graph that Charm++ generates, or the statistics that it can collect in the background. This includes the total messages, the total number of bytes, the external messages or external bytes, that is, how many of these messages or bytes are actually communication with chars on other PEs versus within the same PE. We also look at the average hops because it's something important as you go between different topologies. Machine statistics are also something that that are important primarily to do with communication bandwidth and latency, which would affect the communication cost on that supercomputer. We also provide overhead versus overhead over the benefit of centralized strategy as one of the features to the model. The idea is that if the overhead of load balancing is much higher, if the fraction of overhead by benefit is very high, then you would want to go towards something like distributed. If it's not too high, then it's all right to go towards something that's centralized. So we hope that the random forest algorithm would use these features to make its decision. Some of the features that we generated from these statistics. So some of the statistics we could use as such, but some of them we made into more sensible features that the model could use. So like I mentioned, there's PE load imbalance, which is max load by average load. There's the relative rate of change of load, which is how often does your max load change, and at what rate does it change, and what is the rate at which your average load changes. And then communication cost by computation cost is something that we also generated as a feature. In addition, the overhead is one. This needs to be changed, but the overhead of centralized greedy overhead versus benefit is another characteristic that needs to go in. We theoretically compute the overhead of greedy strategy in general because when an application is running, it doesn't really know how long it took to run the greedy strategy, so we have to compute it based on the number of objects and the number of processors. So this is the training set that we used. This LB test is one of the synthetic benchmarks that's available as part of the Charm++ benchmarks. Some of the tunable parameters that are, you can vary the communication pattern. You can provide, you can ask it to use mesh 2D or mesh 3D or a ring topology for communication between chars. You can change the computation load, you can change the message sizes, you can change the migration cost. So this is one of the test cases that, just to show how different test cases. We performed around 100 runs, and these are a couple of examples of how load balancers would perform for such a synthetic benchmark. So if you look at something that's a communication-intensive synthetic benchmark, the graph on the top, we find that Metis LB is by far the best compared to something like greedy LB or hybrid LB. For a communication-intensive workload among these synthetic benchmark runs, we found that greedy LB performs the best. And in addition, so primarily varying these parameters helped us generate different application characteristics. We could have load imbalance, we could have dynamic load imbalance, wherein over iterations the load imbalance keeps changing. And then we also had a case where where we can have computation intensive workloads versus communication intensive workloads. So we began with testing our accuracy based on prediction of test data. We found that in most cases, we actually found 100% accuracy in the training data set itself, which is we train 75 configurations, and then we make the model predict the result for the 75 configurations. And that was found to have 100% accuracy. We used 25 runs in this synthetic benchmark runs to find out how the prediction was. And we found that in some cases it found the best load balancing strategy, greedy LB. In some cases in most cases for test data set, it found the second to best strategy. This score, when I say second to best, the score is basically the time that predicted LB took divided by the time that the best LB took, -1. So for best LB, the score would be 0. If our predicted LB was the same as our best LB, the score would be 0. So the larger the score, the worse prediction accuracy that we received. This is a histogram of all the 25 synthetic test cases. The histogram shows us the number of how the features were used by all the 100 trees. We found that some of the key features so these are basically features in the internal nodes of the trees that were used for prediction. So some of the key features that we found were the PE load imbalance and average utilization of PEs, and the overhead versus benefit, which was another key feature that we expected the model to pick up. And communication versus computation was another key feature that the model picked up. So quickly moving on to some of the example applications that we tested against. I'm going to talk about Lassen, PRK PIC simulation, and NPV BTMZ. We had a few more benchmarks that we tested against. The Lassen wave propagation application had almost, as you can see in the lower graph, almost all the predictions that were made were close to the best LB. The orange is the predicted LB, and the black is the best LB. So in most cases, if not the best, it was the second best. And we found that for 1024 cores, the predicted LB can perform twice or 2x better than the worst LB. And in this case, the worst LB was refined. And the best LB that was predicted was distributed LB. And then we also found for particle in cell simulation, Champless implementation of the PRK PIC benchmark, that greedy LB was predicted for the core count. Since we ran up to 1024, it was found that all the predicted LBs were greedy LB and all the best LBs were greedy LB. And this also shows more than 2x better performance compared to the worst LB. We also ran NPV BTMZ, wherein I will move on to the scores. So this is the scores here are the speed up that the speed up that the predicted LB has with respect to the best LB. In most cases, it was, at least in in 128 and 256 cores, it was found to be at least the second best, and it predicted between greedy and Scotch, which was kind of also the expected load balancing algorithm we had for NPB, because it's more communication intensive, but it also exposes load imbalance due to uneven zone sizes. For smaller core counts, it was probably not the best because there's a lot of noise and the smaller runs finish very quickly. This is a quick description of so we took the tree that predicted greedy LB with the best, with the highest probability for greedy LB class. In this case, we found that this is just one of the 100 trees for NPB BTMZ. So it seems to have first taken into account LB gain as the root node, and it found that when the LB gain was quite high, it was all right to use a centralized strategy. So it goes towards the right side of the tree. And on the left side, you see that there are examples of distributed LB, which it would have probably taken were the LB gain not high enough. Once we find that the centralized LB gain is high, it looks at the number of PEs. When the number of PEs is low, it tends to go towards the left side of the node, whereas on the right side you have hybrid LB, which is usually better for higher core counts. And then moving on, then it looks at migration overhead, and then it sees that the migration overhead is low. Therefore, it's still acceptable to do greedy LB. If not, it would have probably gone to something like refine LB. Then it looks at the relative rate of average load, and again it finds that this rate is quite low. So it's acceptable again to use greedy LB versus distributed LB. This seemed pretty intuitive and good prediction. So yeah, so that's what we used. So in a nutshell, we used random forest algorithm for training and to predict the suitable load balancing strategy with high accuracy in most cases. And one thing is to be noted that we trained the model based on synthetic runs, and we found it to work for most of the mini applications. We also added support in Meta Balancer for collecting features at runtime and to perform the prediction. And the result analysis added some more confidence in our results as to what the random forest algorithm was doing for predicting the best load balancing strategy.
Questions for Kavitha?
So in these days of machine learning, why random forest and not a neural network of some sort?
It kind of evolved from decision tree kind of, we thought we'd begin with a decision tree, and then I guess random forest algorithm kind of is similar. It's a classifier, and in this case it seemed applicable to select a classifier because there's a small set of load balancing strategies to select from, and a classifier would work well for that.
You showed a histogram of one of the instances of all 30 parameters that you had collected.
Yes.
I noticed there's a lot of duplication in the effectiveness of any given parameter. Did you try doing any sort of dimension reduction?
No, we did something simplistic though. We again took a tree that provides the maximum probability for the correct algorithm, and then we tried to see if, it reduced a lot of noise in comparison. When you use all the trees, then it seems like it's a cumulative thing and it adds up values for a lot of things. But we tried to selectively select trees that predicted the result correctly, and that seemed to reduce the noise. But we have to try other options for reducing the noise.
Beautiful work, thank you. Do you have to run your target application through to completion to collect the statistics?
No.
So at what point does the decision get made which load balancer to use?
So the idea is that this can happen even in the beginning, in the first iteration of the application or the second iteration of the application. Since the model is already trained, MetaBalancer outputs all the features once a single iteration is complete. It can output. Not a whenever the @sync is called. So it depends on the frequency at which @sync is called. It's not a load balancing.
You need
call
some
yet.
data
Yes.
before you can go on, though.
Yes.
I'm thinking of my application that starts out uniform, and then you get structure formation, and that drives load imbalance, that drives load balancing. And it may be that the character of that load imbalance is changing as the problem is evolving. So
Right.
I'm trying to understand at what point in my simulation this would decide which load balancer to use, and would it make a different decision later?
Yeah. So yes. So the user can actually instrument these iterations and decide when to make the @sync calls. They are very low overhead calls. So as the application characteristic changes, MetaBalancer still would be able to capture these changing characteristics. And then if we look at the previous work with MetaBalancer, it knows when to trigger. If it correctly triggers the load balancer, by the time it triggers, it also knows what's the best load balancing strategy to use. And if further down the application there are changing characteristics, MetaBalancer continually monitors those and can
Great.
still
Okay,
invoke the
beautiful.
load balance.
Thank you.
So the decision tree, does it need to be retrained for different systems and architectures, or you think the same tree can be used for different systems as well?
So the only additional feature that we use for calculating communication cost is the latency and bandwidth. So and then we feed it into it, but we haven't actually tested it across different systems. So it's possible that it would require more training. Most of our runs were made on Blue Waters. But
All right, any other questions?
I think there's a potential for confusion here, as indicated by the last question. You are not using a single decision tree. You drew one picture of a decision tree in between to show, and that was the actual algorithm is a forest of decision trees, which use hundreds of decision trees and takes a vote from each decision tree and somehow combines those votes to decide what to do, correct?
yes,
And that's all happening automatically inside this algorithm.
yes, yes.
So just wanted to make that clear, okay?
All right, let's thank Kavitha again.